Thank you for the invitation, first of all, to speak. Nordic Structures, I'll just give a brief introduction on our company. We're not a very well-known entity out here on the West Coast. Our company, unlike Stora, we're not 700 years old. We have a long and storied history, but it starts in 1961, making mining timbers in northern Quebec, and that's pretty big for that business. The area that we harvest in really defines the mission or the steps that have led to the evolution of Nordic Structures. We're in a microclimate that has a growing season of about 50 days. So our trees grow vertically very quickly, but they don't grow out very quickly. And at 80 to 120 years old, they only average 4.5 inches in diameter. So I would just ask that you bear that in mind as you look at the proof of concept that we have on this really amazing structure that we're going to walk through the visionary portion from the architect that developed it, and then walk through the engineering and the challenges that were defined in order to bring this to reality. So it's really quite an interesting process. And I think the fiber is really what dictates who our company is and what our path to market has been. We started manufacturing engineered wood products in the 1990s, making I-joists with solid sawn flanges, and then moved into glue laminated production. And we did it with a standard that didn't exist at the time. We started creating glue lam beams with small component sections of black spruce. It's a tree that grows in peat bogs. As I mentioned, it doesn't grow very large very quickly, but that fiber density gives it really tremendous strength. And our process is really driven to create value and push it upstream. We don't have really phenomenal initial product to draw from and then create these wonderful pieces out of. So we have to drive that upstream and create value that way, rather than making just furring strips and cribbing and pulp. So our processes have really led to the refinement of these products and bringing elements to the market that really didn't exist before. The stick-to-itiveness and the spirit of innovation that really drives our company. So since 2000, we've been making glue lams. In 2009, we built our first CLT plant and started cranking out panels in 2010. And we had a Field of Dreams mission. We figured if we build it, they will come. We had done the research in Europe. We definitely saw a path to market for cross-laminated timber, and that would be our next saving grace. And unfortunately, the rest of the market didn't really read the same newsletter that we did. So we didn't have people beating a path to our door to buy CLT. So we ended up developing our own first product and built a 4-story, 24-unit condo project in northern Quebec in 22 working days with 4 guys that had never built using the product before. This was in the weeks between Christmas and the second week of February. So cold, dark days. So if there's one thing that it'll tell you about CLT is that there's no real building season with it. It's great for playing hockey up there. You can do that all winter, but you can also build all winter. So we'll get into the process. This structure was really defined by the city of Montreal. Had a brownfield site. It was actually a gravel pit for a company that worked in an industry that's affiliated with business, but it's not wood. And this gravel pit was basically left untouched after all the good gravel was extracted, and it's in a nice area in the north part of Montreal that's becoming really developed for. People moving up in the community, and they wanted to do something with that and turn it into an eco-park. And so Société Perrot, amongst 30 other people that were candidates for the project, had visited the site and looked at it. So this is, I don't know if I got a. There we go. Okay, so that's it. If anyone's ever been to Montreal, that's right on Papineau Boulevard, north of the Met. Montreal is the only city that's oriented where the sun sets in the north. This is the way the north runs in Montreal. It's obviously, this is east-west. But the the sun actually sets in the north the way our city is oriented. So that's the North Island. Our office is actually just out here, south part of Montreal. The project itself is on this site, and the design was really driven by looking from across the street at the shale strata. And the architect looked at the shots of quartz through the shale and came up with this look. And so that really is what informed the visionary process of defining the roof system for this massive soccer stadium. And interestingly enough, this was the only wood option that was offered to the city. Every other designer came in with a steel and concrete option. And so the intent was to drive something that was really unique and spoke of the industry in Quebec and moving forward, but also giving a little bit of uniqueness to the project. So this is really, Nick was talking about the hybrid projects and the baseline projects and the boutique projects. This would be your ultimate boutique project. And it drove some really unique engineering challenges and manufacturing challenges that we'll be getting into. As part of this, you're looking at basically 256-foot clear span, and the cantilevers on this building are probably the longest wood cantilevers on a roof system currently in existence. They're 13 meters, so 50 feet in one axis and 30 feet in the other. So the bidirectionality of cross-laminated timber is really brought to good use here. So the intent here was to drive that 256-foot clear span. There were 13 main carrying beams in the project. Steel and concrete was going to be the base form for the structure. We were going to deliver the roof system all in wood. And so part of that was the fact that we're talking about manufacturing off-site, optimizing, creating something that's going to get delivered to the job site just in time, using conventional equipment without having to have a ton of helicopter deliveries or things of that nature. We're 550 miles from Montreal, so we had to take into consideration the logistics of driving through small secondary highway systems and delivering it to a job site in a very highly traffic-oriented urban setting. So it offered no set of small challenges. Capacity-wise, we can make beams as long as we need to, as long as we can, continue to crank it out. But the limitations for us were to make 80 and 84-foot sections in the process. So we created a box beam. Without boring you, I'm sure there's some engineers in here that'll really geek out on some of the stuff that we did. So I'll highlight it. The architects will probably like to know that their vision can be translated into something definable. And this is really what we're looking at. Again, 13 main carrying beams. There are some cross members that are replicating that quartz running through the shale, and so they really don't have any structural impact other than keeping the base of those deep beams from flexing, and then the cantilevers on the structure. So our process was to create box beams, basically big caissons. We were using very deep glulam cross sections, and then using cross-laminated timber as a webbing material to drive these beams. So we're looking at basically 84-foot long sections that were going to be recombined and unified at the job site. They're 14 feet deep. Okay, so it's not your lean building project like we like to talk about, but it does show that you can, what is possible to extract with a visionary process and a proof of concept that sometimes it's nice for the engineers that work in our office to have something to really sink their teeth into. And this worked out to a little bit over 2 years worth of engineering. So 4,000 some odd hours in this roof system. So we're looking at a couple of end sections. We didn't have enough challenges with making a beam 256 feet long. The architect decided that he wanted to put the openings for the ducts rather than in the middle where shear was less. He wanted to put them at the extreme ends where shear is greatest, and challenge number one. So that gave us some opportunity to flex a little bit and do some high-end analytics with our structure. So we did a finite element analysis and determined how we were going to be able to build this. Again, the elements you can see here where we have the wood beam on the bottom, wood beam on the top, and then the cross-laminated timber in the core. That's the webbing to separate it. And we had to put in a shear element in steel. And so the process to drive that was to determine what was going to be the limiting characteristics of the product. So we had to determine the shear strength of the glulam, as well as the assembly, and then the plane shear in the CLT, and then the rolling shear that also helped define it. And so basically we were looking at process. Montreal, we get a little bit of snow. It's not quite as bad as in Chibougamau where our plant is. We get maybe 10 or 12 feet of snow. In Montreal, it's probably 8 or 9 feet. But the loads developed on this are the equivalent of 10,000 kilonewtons in tension at that construction joint. So these are joints that were necessitated by the overall length of the beams, and marrying them together. 10,000 kilonewtons, it would equate to 2.6 million pounds of tension in these beams. So it's a very heavy load. And as if we didn't have enough challenges, with our wood fiber being so small, we can't really always orient the product in a lateral fashion like you would normally see with glulams. Typically, you're going to see 2x6, 2x8, 2x10 that are laid flat. And so you want to distribute that load, and you're going to connect perpendicular to the grain. That's where your strength is. Our wood cross sections are very small. They can go as small as 3/4 of an inch by 1.5 inches, and then they're recombined. And so we decided to make the challenge a little bit better. We were going to connect into end grain. And the engineers and staff know that you don't do that with wood, but we're up for a challenge. So we figured there's a way we can do this and process it. And it is a little mind-blowing if you've ever done wood analytics before. But this is the cutout area for the passage of mechanical ducts. Again, we use steel here, so it's a little bit of a hybrid system. And the proof of concept for our box beam was driven by this wood bridge that we built in northern Quebec. This is on a logging and mining road that goes up to the big hydro projects in northern Quebec. That's 14 feet deep. It's 78 meters, 240 feet long. And it's the longest simple span wood bridge in the world right now. And it takes commercial, actually it's industrial loads, 192 metric tons. So when we did the analysis on this, they were taking the transit and watching these very heavily loaded gravel trucks and lumber trucks crossing over. And the limitation for us was that we're in an area where there's a lot of indigenous people. They had to be able to stand up on their canoes as they were going under the bridge. So that was built with that in mind at the height of flood season. So the intent being that we didn't want to put a lot of concrete in there and then have these people be cut off from one area of their hunting grounds to others. So a lot of our process is defined by the relationship we have with the indigenous people in the north. I failed to mention that we're an FSC certified manufacturer, so all those elements are taken into account when we're doing our extraction. So the proof of concept was done there, and basically you can see that we were able to connect into end grain. Of course, the loads that were developed are not going to be as severe as we had on the roof. And then we had the connection. These are knife plates that we're able to screw into, and basically, the volume of screws that we're going to put in is going to offset the tension loads that are in that. And so the combination of both of those elements, we had the vertical cross-laminated timber and glulam box beam, along with the pin connections that were allowing us to do these 210-foot clear span arches for soccer stadiums and things of that nature. That really drove the concept here. So we had some analytics done, and we found that we could do that, and the size of the connections are pretty significant. I mean, we're looking at 4-foot deep steel members there, and the pin is 150 millimeters. So, Doug, what would that be in inches? Help me out here. I'm drawing a. Is it 6? A little more? Yeah. Okay. So 6 inches in diameter. So it's a nice big piece. We'll see the actual thing in process here. So we looked at the different types of connections, as I mentioned, and we determined that rather than go with glued rods and other types, we were going to work with screws. The limitation, again, being the fiber density of our product and the amount of tension that we had to offset. We calculated that we could do it if we used screws at a 12.5-degree angle with a 1/2 inch diameter, 25 inches long, and we needed 416 of those for every beam that comprised that. So what that allowed us to do was analytically determine that we could have failure within the steel that was going to be the determining factor, that the wood wouldn't fail. And this was a screw that did not exist in the world, and we have a good working relationship with SWG. They actually built, they co-designed it with us and built it specifically for this job. And then the connections, here you can see the overall loads. The screws are at a slight angle, again 416 per member. These steel elements that allow the screws to hold on to the end of the beam were built at our plant. We have a little steel fab shop, and that allowed us to pre-model and actually test out ahead of time before we sent these pieces out to be actually destroyed at a lab in order to prove the concept. And so what we did is we basically built a half-scale model with half the screws. We didn't have any testing facilities here in North America that really could generate the types of tension loads that we needed to prove the concept. So we shipped a series of those beam sections to Stuttgart in Germany, where they have a plant, and brought these steel members, and were able to develop that load, that 10,000 kilonewton load. We tried to get local firms to do it, but they couldn't. So we shipped this off to Germany. You saw the 3 beams there. This is the equipment that we needed to be able to actually do the testing. Part of that was actually building a template that would allow us to drill the same degree of hole at every one of those 416 unique locations that we needed to. And also take into account the torque of a drill of that length that was going to deviate, and so we had to have a really specific drilling sequence and drilling timing in order to afford that. So we would actually do it in thirds of stages. Start, and then we had a visual inspection. We had to have a second person there timing it so that we would not over torque the screws. And there was a hollow bit that allowed us to blow air through it and push the wood shavings out as we were doing this. So a 3-step process. This was also done proof of concept at our plant. And then when we went to Germany to do this, we brought the biggest guy that we had with the biggest arms, and he was the one that screwed in our sample pieces. And you can see the product going into the press, and then you can see the product coming out of the press. And the good news is that there are a couple of grain tear-outs that you can see at the top and at the bottom, but the rest of it, it's all the screws have sheared off. So this was a huge aha moment, a yay moment, that we didn't waste all that time and then have the wood fail. That the proof of concept engineering actually proved out in a real world scenario. So then we went to full scale fabrication. We're looking at 4,000 cubic meters of wood. We built it in 3 sections. Again, this was a hybrid structure. It wasn't all wood. The wood roof was all wood, but then the structure itself was steel, concrete, and glass. And in building it in 3 sections, just like Nick was saying, you're doing just-in-time delivery. You want to make sure that you get every element to the job site in sequence so that it's not sitting there, getting dirty or being abused by the workers on site. Not that they would ever do that. Just thinking out loud here. Anyway, so then we had to build them, and the good thing is that next to our press, we actually had just enough room to lay them out and do test fittings before we finished wrapping them. So the concept here was that we made our glulam box beam components, and then we took the CLT and we built one layer. And then we screwed it in with our sacrificial piece that was kind of the element that was going to hold the steel in the interim. And rather than have a different component design from one section to the other, even though the holes for the ductwork were only on one side of the building, we decided that it would be more effective, more efficient to have just two designs, one for the center beam and then the others for the extremities. That way they could be interchanged if needed. And so this was built over time, 2 series of operations. And you can see the guys that are working, they call this our chair place where we have to do cold press beams. All the individual component segments of those glulams are actually manufactured in a hot press. And then the individual components are brought over to this large section where they're cold processed. So it's more of a time component where the glue is curing over time as opposed to the RF frequency that we use for the component elements. And again, these are all components that are basically 1.5 inches square, so very small pieces. You can see the machining done. We have 3 robots that we operate with, a couple of Supremas and a SCM machinery in our shop. Here you can see the guys working on the assembly. And then to ensure that we had good pressure and good contact during the glue, we used these humongous rods to keep the pressure on. Then lifted them into place to make sure that they had the integrity that they were going to need. Then wrapped them and shipped them to the job site. So you can see a test being done here on the final assembly of the glue. We're putting 2 parts together. This shows the extremity of the beam here. Okay, and again, this detail was replicated on both sets of the outside of the beam structure. When you see this, the GC on the job came up to the plant and we told him that we actually had the construction site put under roof so he could practice before he had to actually put these things together in the field. This is a picture of the template of the drilling mechanism that we developed for this project. And again, we wanted to make sure that the drill was properly aligned and that the angle was consistent. So when you're doing that 416 times, we had 2 people working on shift. One would actually operate the equipment, and the other one would sit there with the timer, and then they'd spell each other every couple of holes. And you can see here what it looked like, those 416 screws. I don't think the guys really looked forward to that when they started their day. When they finished, they were probably really happy. And here you can see the visual inspection that we had to do to make sure there was no deviation of that drill hole. So you didn't want that screw to migrate and then be off. It would have created fiber destruction, and that could have been compromised the beams. So again, this 3-part process, we actually had to monitor it by frequency of sound. If we heard the drill starting to make a funny noise, we would stop and then pull back, and that could be either because the drill was getting too hot or it was operating at a different angle. Sometimes you have to have a musical ear. It becomes a little bit of alchemy actually in the process. So it was a really, really interesting process to have to go through. And there's the completed steel plate after the screw application. And now we're doing the test fitting of the 6-inch diameter steel connecting plate. A week before the shipment, we wanted to make sure that we were doing this, and that's our installer come out to the mill and see the process so that he would be aware of it. How many? 3 minutes? Okay, so I'll run through this pretty quickly. So we have here you can see the completed assembly. And then to the job site, every one of these massive three-piece beams were shipped in individual components, of course, lifted out of place using container loading equipment. And then the assembly, we actually had to do that. It was an orchestrated assembly again. We put the three pieces down on platforms and then build it. And then after it was built, we would tilt it up and support it. And then we had an engineered lift whereby we had two 50-ton lifts. These are 100-ton beams. So we had two 50-ton lifts that were at the extremities, and then we had a third one there for as a support mechanism in case there was a failure. And it was a really big deal in Montreal. The largest beam to be installed on a public project was what they called the mega beam on the Champlain Bridge years prior. And this beam was actually longer than that. So there were news people that came out. So we had the local newspaper photographer actually took a picture of this. So here you can see it in place. This is what it looked like. Again, I mentioned that some of these visual elements, provide some lateral stability for those glue lamps, but they don't really perform a lot of structural intent. The beams themselves supported the entire roof load. Here you can see what it looks like over time. We did have some delays on the job, but it was based on steel deliveries on the job site, not the wood. So we actually had to slow down our delivery at one point to the job. And here you can see the cantilevered application. And again, talking about the bespoke or custom boutique applications that Nick was talking about, we had to find a way to connect two distinct cantilevers of different lengths and get those processes, those elements tied together at the same point. And when we did our laser analysis, when we took the transit on it, we were inside a dime on that. So it was really a tremendous moment for the designers on the team to see that when we went out to do our surveying. And here you see the finished product. I think that looks kind of cool. The architect really was proud of his vision, but he wanted all that wood to be all wood. So we ended up cladding those joints, which I think may have been a little bit of an opportunity lost to really talk about it, but it does look kind of interesting to have that all. This is before cladding, and just to give you an idea of the scale, this guy here is 6'3". Okay, so that's those are really deep beams. It's a very unique project. Here you can see the installation of some of the cantilever elements on the outside. After that was done, we have shoulders at the back end of the project that actually defined the opening for the outdoor soccer stadium that is attached to this. So we'll go quickly through that because I'm running out of time. And you can see these here beams, they're about 8 feet deep. And they take some of the lateral load and put it into buttresses at the extremities. So here's the finished product. I think this, it's nice to have a boutique project like this for our engineers to be able to spread their wings a little bit and do a proof of concept. If I can paraphrase Peter Venkman from Ghostbusters fame, there's no project too big, no budget too big. Unfortunately, they don't happen that way very often. So mostly we try to drive budget on our projects. This was one where it was maybe a little bit less of a concern. It was really something that we had a lot of support from the city, from the designers, from the engineering people that worked with us on this, and the construction crews. So it's really a gem in the north side of Montreal. And we have a cast of thousands really that we should thank for that. Unfortunately, we don't have time, so I think we'll just say hello and thank you to all of those people for the work that they did with us and allowing us to deliver something really, really unique and really push the limits of what's possible with cross-laminated timber and mass timber. Thank you.